Good morning to our beloved lecturers. We are from Group 9 and today we would like to present about our project, which is Simulation of Industrial Robotic Arms by using ROS. First of all, allow me to introduce about ROS. ROS, which is known as Robot Operating System, is an open source and meta operating system for robots. It is widely used in building robotic applications through access to a large set of open source software and tools. ROS is originally developed in 2007 at the Stanford Artificial Intelligence Laboratory and its development continued at Willow Garage. It is managed by OSRF, which is known as Open Source Robotics Foundation, since 2013. ROS is important to us. Those are some importance of ROS. First of all, ROS can provide services which are designed for heterogeneous computer clusters such as hardware abstraction and low-level device control. Besides, ROS can also provide services such as implementation of commonly used functionality, message passing between processors, and package management. Last but not least, ROS also can provide tools and libraries to obtain, build, write and run the code across multiple computers. Generally, software in ROS ecosystem can be separated into three categories. First, language and platform independent tools used for building and distributing ROS-based software. Second, ROS client library implementations such as ROS CPP, ROS PY, and ROS LISP. Third, packages containing application-related code which uses one or more ROS client libraries. There are several advantages of ROS can provide for us. First, ROS is a large community and open source, which we can easily try other people's work and share our work for others. Besides, ROS can provide a lot of infrastructure, tools, and capabilities. There are some disadvantages of ROS too. First, security and scalability of ROS are not emphasized. Besides, some platforms other than Ubuntu Linux platforms are not well supported. Last but not least, ROS is not suitable for mission-critical tasks.
For our project, we have to install the Ubuntu. In our computer, we have installed the Ubuntu version 18.04, and also we also install the ROS Melodic and move it inside our computer by using the Ubuntu. So now we have to start using the move it, and we also, before we start the move it, we have to git clone the URDF file from the GitHub of our robot. So for our project, we have used the ABB 1600 IRB robot. So now I have to start my movie setup assistant. Let's launch it, and then now we can see the movie assistant. So we have to create the new movie configuration package, and then we browse it and find the URDF file that we git clone from the GitHub. So I place it at the document there. Okay, so as you can see, the IRB 1600 ID URDF file. So we have inserted into the movie as setup assistant, and we load it. After we load the robot URDF file, we can see the robot at the right side there. So this is our robot, IRB 1600. So we have to self-collision it. So in order to generate all the join and link of our robot, so we can see all the link parts in our robot. And then we have to define a virtual join. The virtual join is like a base of our robot. We can choose it has different type. For our project is fixed, it will go away. So we can name the parent frame as the world. After we should define the virtual join, we can define the planning groups. So the group for our project we have two groups. One is the manipulator, all the joints that can move. So now we have to create the manipulator groups. So name it as manipulator. For the manipulator, the kinematic solver will be always the KTL kinematics. So we have to add the joints, specify which joint is the manipulator. So we have to, in our project, there is 1 to 6 joint is the manipulator. And then we also have to add the grip, another planning groups, which is the grippers. So for the grippers, we have to, same like just now, we have to add the specified link. Then save it. And then we can define the robot poses. For example, we got two poses. One is the stand as the default, the robot is standing there. And the second one, we can maybe add something like work. Okay, and then we can play around the drawing there to choose to adjust it at the most suitable position that you think. After that, after we adjust it, okay, we save it. Then next we have to define the end effector, which is the grippers. There is only grippers inside our end effectors. So we can name the end effector name as the gripping tools. So the end effector groups must be the grippers, and then the parents group as an optional, so we no need to choose it. And for the basics, define the basic joints. Basic joints is the joints that is not actuated by the robot. For example, we can say it's like electric scooter that it has the caster wheel, and the caster wheel is not actuated by the handle. So there is an example of the passage joint. For our project, we don't have any passage joint. So after that, we can use the movie to generate a new URDF file so that we can simulate with the gazebo. So we copy it, we can use it later, and then we have to fill in the author information, and then finally we can generate the configuration files. So for our project I have done before, so I will just let's see as an example. You can browse and choose the location of the file and then generate the package. After we have generate the configuration file, we can start to input the configuration file into the RVIZ so that we can planning movement of our robot. So we can see in our project we have already done the RVIZ about the planning motion, and then the robot also moved very well. So this is the RVIZ result, and then we have to simulate it, the robot inside the gazebo. So now we will enter the tutorial robot inside our gazebo. I will show the tutorial robot that we do before inside the gazebo. So we enter the code of the tutorial robot, and then yes, the gazebo is opening, and then yes, the tutorial robot is simulated inside the gazebo. As we can see, the robot is simulated and is functioning inside the gazebo. Now we have to input our project robot inside the gazebo, and we have to spawn the model. So we have put the command inside, and then we have to make sure that the z is 0, so that make sure the word is on the origin 000, and then we have to input the file that the URDF file that we generated from the move it as setup assistant we do before, just now, and then we have to place the path of the file which we place for our project. We have placed inside the documents, and then name it as the app.urdf file. Yes, as and inside the gazebo, the robot of our project has been simulated. Thank you.